Imagine you're floating in space. No ship, no suit, just you and the infinite dark. And then you notice something. A region of space that seems wrong. Stars bend around it. Light curves toward it. Nothing comes out. You're drifting toward a black hole. And here's the thing nobody tells you. You wouldn't even know you'd crossed the point of no return. Before we fall in, we need to understand what we're falling into. A black hole is not a hole. It's not empty space. It's the opposite. It's the most concentrated mass in the universe. A point where gravity becomes so extreme that the very fabric of space-time collapses in on itself. Here's how one forms. When a massive star, we're talking at least 20 times the size of our sun, runs out of fuel, it can no longer hold itself up against its own gravity. The outer layers explode outward in a supernova. But the core collapses. In less than a second, something the size of a city compresses into a point smaller than an atom. That's a singularity, the center of a black hole. A place where our known laws of physics simply stop working. Around it forms the event horizon, the point of no return, the boundary where escape velocity exceeds the speed of light. And since nothing, not even light, can travel faster than light, nothing gets out. Not light, not information, not you. So, you're falling in. Let's say it's a supermassive black hole, the kind found at the center of galaxies. Some of these are billions of times more massive than our sun. Why does size matter? Because of something called tidal forces. With a small black hole, the gravity difference between your head and your feet would be so extreme that you'd be stretched like spaghetti, literally, before you ever reached the event horizon. Scientists have a name for this: spaghettification. That's a real term, used by real physicists. But with a supermassive black hole, the event horizon is so vast, sometimes larger than our entire solar system, that the tidal forces near it are actually gentle. You'd cross the point of no return without feeling a thing. No alarm, no signal, no warning. Just stars bending. Light from distant galaxies warping around you into halos. The universe behind you compressing into a single bright ring as you sink deeper. And then, the event horizon. You cross it. And from this moment forward, falling deeper is as inevitable as time moving forward. There is no up anymore. Every direction leads to the singularity. Physics itself has redirected you. Here's where it gets truly strange. Because what you experience falling in and what someone watching you from outside are completely different realities. This is because of gravitational time dilation, one of Einstein's most mind-bending predictions. The stronger gravity is, the slower time moves. Near a black hole, gravity is almost incomprehensibly strong. So, from the perspective of someone watching you fall, let's say a friend in a ship at a safe distance, they would never see you cross the event horizon. As you approach it, they would watch you slow down, redshift, fade. The light reaching them from you would stretch out, grow dimmer, more red. You'd appear to freeze, hanging at the edge for eternity. Eventually, you'd fade out entirely, not because you stopped, but because the last photons of light bouncing off you could barely escape the gravity well. To them, you vanished at the edge of time. To you, you fell straight through, in finite time, without even noticing. Two observers, two completely different experiences of the same event. Welcome to general relativity. Now we enter territory where physics becomes uncertain. Because no information can escape a black hole, we can't directly observe what happens inside. Everything from here is theoretical. But here's what our best models suggest. Time and space swap roles inside a black hole. Outside, you can move freely in space, but time always moves forward. Inside the event horizon, your movement through space becomes mandatory, specifically, movement toward the singularity. Just as you can't stop time outside, you can't stop your spatial fall toward the center. The singularity approaches, not like a wall, more like a future moment you can't avoid. Our equations suggest that at the singularity, tidal forces become infinite. All matter is compressed into an infinitely dense point. Everything you ever were, atoms, memories, mass, would be added to the singularity. But here's the problem. Infinity in physics usually means our model is broken. When equations give you infinity, it's typically a sign that the theory isn't complete. General relativity, the framework that predicted black holes, breaks down at the singularity. It can't tell us what actually happens there. That's where we need a theory of quantum gravity, a unified framework that bridges general relativity and quantum mechanics, something we don't fully have yet. So the honest answer to what happens at the singularity is, we don't know. The universe has drawn a curtain around its deepest secret. In 1974, Stephen Hawking dropped a bombshell on the physics community. He showed that black holes aren't completely black. Due to quantum effects near the event horizon, pairs of virtual particles constantly pop in and out of existence at the boundary. Normally, they annihilate each other immediately. But at the event horizon, sometimes one particle falls in and one escapes. The escaping particle carries energy away from the black hole. Over an almost incomprehensibly long timescale, this Hawking radiation causes the black hole to slowly lose mass, to evaporate. A black hole the mass of our Sun would take longer than the current age of the universe to evaporate. A supermassive one? Incomprehensibly longer, but eventually gone. And this creates one of the deepest unsolved problems in all of physics, the information paradox. Quantum mechanics says information can never be truly destroyed. Every particle carries information about its past state. But if a black hole evaporates via Hawking radiation, and Hawking radiation appears to be random, carrying no information about what fell in, then where did the information go? Did it get destroyed? That would violate quantum mechanics. Did it survive somehow? If so, how? This paradox has consumed the careers of some of the greatest physicists alive. Hawking himself changed his position on it multiple times. It remains unsolved. Black holes aren't just cosmic curiosities. They're windows into the deepest questions about the nature of reality. They tell us that space and time are not fixed. They bend, warp, stretch, and collapse. That the laws of physics we rely on every day aren't the final story. That at extreme enough scales, everything we think we understand breaks down. And perhaps most hauntingly, they suggest that the universe contains things that are fundamentally unknowable to outside observers. There are regions of space-time, right now, scattered across the universe, where information enters and never returns. Where events unfold that no one outside will ever witness. Black holes are the universe's sealed rooms. And we're standing at the door, pressing our ear to the wall. So, what happens when you fall into a black hole? You cross an invisible boundary without knowing it. Time bends around you, the universe distorts into alien geometry, and somewhere at the center, at the singularity, physics stops giving us answers. The black hole keeps its secrets. But here's what I find beautiful about that. Every unanswered question is an invitation, an open door. Black holes pushed Einstein, they consumed Hawking. They're pushing the physicists alive today to reach beyond what we know. The universe is stranger than we imagined, and we're only just beginning to understand why. If you want to keep going deeper, subscribe. Next week, we're asking a question that's kept physicists up at night for decades. Is there anything on the other side of a black hole? See you in the void.